In this video, I want to discuss the kinetic theory of gases, which are ideas that are brought about by different people at different points of time. And the first one of the postulates for kinetic theory of gases goes back to the idea that I put forward when we first began this discussion on gases, that gases have what is called as random motion. Random motion. So when we use the word random motion, it basically means that the gas molecules are going to move very quickly, very fast in variable directions, in all directions, and with variable speeds. So that is to say that both the direction as well as the speed of the molecules is going to be different. What that ultimately means is that the properties that will be dependent on the molecular motion are going to be the same in all directions, and so you will have to study things like pressure, things like temperature for the overall average for that gas sample. You can't say that one particular gas molecule is at, let's say, 1 atmospheric pressure, it's exerting 1 atmospheric pressure, and there is another one at 2. You have to study that as an overall average for that particular gas sample. The second postulate essentially talks about the volume, the particle volume. And in that, it states that particle volume of a given gas sample is negligible. It's much, much, much lesser than the total gas volume. And that makes sense because if you think about what we learned about gases early on, gases tend to occupy the entire space that is available to them. What does that mean? Hopefully you can realize that this means that essentially majority of the space in case of a gas sample is empty. So I'm just going to draw a sample of gas. You have a little molecule here, another molecule here, another here, another here, another here. So let's say you have a gas sample and there are these molecules that are present in it. Notice majority of the area that's present, that's the part in white, that is just empty space. There's nothing there. And that's just the distance between the various different molecules, and so one can say that the particle volume is so small that you can actually ignore. This particle volume is so tiny that you can actually ignore that as compared to the volume of the entire gas sample. And so even if somebody says that the volume of gas is, let's say, 5 liters, that does not mean that that the total volume of all the particles put together is 5 liters. It just means that those molecules in that sample, whether it's a container or whether it's a balloon, they're just occupying three-dimensionally, they're just occupying 5 liter of space, 5 liter of volume. I want you to think about this and keep that on the back burner, because I'm going to visit this idea a little later in perhaps another video where we are going to take a look at the exceptions of when this postulate will not be followed. The third postulate that I want to talk about talks about the average kinetic energy of the molecules, that is proportional to the temperature. Now realize for any scientific study we are going to measure the temperature in Kelvin, and one can say that as you increase the kinetic, so as I was saying, that if we increase the temperature, you're basically going to impart more and more energy into your sample, and that would mean that the molecules will start moving really fast, and so the kinetic energy, which is the energy by virtue of motion in any object, that is going to increase as well. So that's a direct relationship between kinetic energy and temperature. Just the one thing that I would want to say here is that the temperature must be measured in Kelvin. The fourth postulate is about gas collisions, that gas collisions are elastic in nature. Recall from physics what elastic collisions are. Elastic collisions are essentially those where the kinetic energy remains constant. There is no loss in energy when that collision occurs. In terms of real life, if you were to think about collision, maybe think about the spheres on a pool table. And let's say there's one ball from here, one from here, that's coming in, they're going to eventually collide, and then they're going to continue to move. If they continue to move such that there is no net loss of energy, you would say that that motion is elastic. Compare the situation to maybe a sphere made of putty, carpenter's putty or something like that. And now if you take those two and you try to kind of roll it over, what happens? It just kind of goes with a thud and it stops to move. Why does it stop to move? Because the collision is essentially elastic, non-elastic, and the kinetic energy is going to be lost. It would just come to a stop. So that is why we say that the latter case is the case of the non-elastic collision. The last postulate that one might be able to take a look at would be about forces of interaction. Forces of interaction. And these could be attractive forces as well as repulsive forces, but essentially this postulate kind of derives its information from the second postulate where we talked about particle volume, and we said that the volume of the particles is negligible because they are so far apart. And in this case, we are going to discuss forces of interaction and see how the forces of interaction are negligible for gas molecules. There is no attraction, no repulsion. You can say that molecules are almost oblivious to the presence of each other. And that just basically means that since the forces of interaction are so little, is basically because the distance between the particles is a lot. I want to keep this last one also on the back burner because we are going to these two, the point number 2 and point number 5, they kind of go hand in hand, and I would want to discuss that a little later in another video as to when these do not hold true.